Today we're going to finish our classroom discussion of Euclidean geometry. We have many more things to take a look at after spring break. We're going to move into neutral geometry next. We're going to finish our discussion of Euclidean geometry with our classroom information today. We're going to start with the crossbar theorem. There we go. All right, the crossbar theorem says, it's based on the betweenness. Maybe go back to the betweenness real quick just to remind us from where we were before. We had a ray that was between two other rays. If they were not opposite rays and the point that it went through from the vertex was interior to the angle. So that was what betweenness meant for rays. And then we have this one based upon that. If ray AD is between rays AC and AB, then AB, the ray AB, will intersect the segment BC. And we'll do a picture to justify sort of at least the visual argument that's taking place first. And then we'll do a formal proof for why that works. So here is my angle where I have my rays. So here's the ray on the top, A. We'll put AB on the top. We'll put AC on the bottom, although of course it doesn't make any difference. And then ray AD is supposed to be somewhere in between them. So here's ray AD. And this says that what should be happening here is that segment BC is intersected by ray AD. And visually speaking, you all say, yeah, it looks good to me, right? So that's what we're going to be proving to start out with this morning, is that actually works. So to start with, we're going to write down some of the information we were given. So by hypothesis and definition of betweenness, what can we say about the point D? Where is it? The ray AD is between ray AB and AC, but what can we say about the point D?
Is it on the opposite side of A?
No, we have to have a line to talk about sides, and we don't have a line yet. Take a look at the definition here. What does it say about D?
It's interior.
Yeah, it's an interior point. That's important. If the point D were on the exterior, you can see sort of visually speaking, if D were out here, like that, it wouldn't necessarily, right, especially if it were over, say, here. It could be parallel to that segment, and it certainly wouldn't be intersecting the segment itself. And so the fact that it's interior matters to our discussion. So D is interior, or you could say is an interior point. D is in, I'm going to say is in the interior. Of our angle CAB. All right, so we're going to let E be a point such that E star A star C, oops, E star A star C and by axiom B2, the second betweenness axiom, this point is guaranteed, so this point exists. Since line AD intersects segment EC in a point A, between E and C. Sorry, my throat is acting funny today. I'll draw in this picture in a minute. We know that E and C are on opposite sides of line AB. All right, so let's see if I can get my picture drawn in well. All right, so we've got a line AC, and we're extending it to include, from our ray viewpoint, to include a point E on the other side of AC. Right? Line AD intersects EC. Did I draw that right? Yeah. And then I've got line AD it's talking about as well. Let me draw it in another color for reference. Line AD will intersect segment EC at point A, and point A lies between E and C. That means that E and C are on opposite sides of line AB. And we could draw in line AB as well, I suppose. Got lots of lines in my picture at this point. That's probably why I don't have a picture in my notes itself. It's because it was a mess. Okay, everybody good so far? We've got things on either side of a line segment, or of a line, excuse me. All right, so proposition 3.8 from last time. So by proposition 3.8, part C, this point B is in the interior of angle DAE. Hence, B and E are on the same side of line AD. By the definition of interior of an angle. Okay, so we've got angle DAE. I don't want to draw it in anymore because I'm making a mess out of my diagram, so I'll draw it and then I'll erase it. I can't draw in that color. It's too dark. Dark purple. So here's DAE, and B is in the interior, right? So B and E are on the same side of a line, the blue line, line AD. Okay, I think I'm going to go to my next slide. It had some more space. All right. Thus, B and C are on opposite sides of line AD. By the corollary to axiom B4. Right, B and C are on opposite sides of line AD, which is what I drew in blue. And we need the B and C to be on opposite sides of that line so that we can actually say that those lines cross. Not only do we need those lines, that line and that line segment to cross, but we actually have to have the crossing place of that lie along the right ray AD itself. Those are the things that we need to still prove. Okay, that they cross in fact, and that the point that they cross actually still lies along line AD, or on ray AD. All right, so we're going to let G be the point between B and C that lies on AD. And like I mentioned before, we know this point exists by the definition of opposite sides. By proposition 3.7, G is in the interior of angle CAB. So by proposition 3.4, G lies either on ray AD or ray DA, the opposite ray. So we're going to eliminate the possibility that that it's on that opposite ray. So suppose that it does, and let's find ourselves a problem. So suppose G lies on DA, which would be on the opposite side of where we expect it to be and intend for it to be. If so, then G is not in the interior. Of our angle. And that is by proposition 3.8b. And that's a contradiction. Thus, G lies on AD. So we had quite a few same side, opposite side arguments within here. A lot of our propositions that used those facts as well. So that we could get the fact that they do in fact intersect, but it intersects the line, and we needed specifically for it to intersect the ray. So we need to be on one specific side of the line, so to speak. The ray that was AD and not the ray that was DA. And so we came up with a contradiction at the very end.
I have a question.
Yes, ma'am.
You put a lot of propositions in there.
Yeah.
Do we have a list of these?
I gave them all when we did them in class last time. So they should be in your notes. Yeah. So if you go back through, like here's proposition 3.8. I think we cited both B and C on this particular argument. We have, there's proposition 3.7. The propositions are all in your notes, 3.6, 3.5. Our axioms and the things that I handed out last time are all on this sheet.
Okay.
Okay, and we will be getting to more of these today too.
The propositions are in the book too, right?
Yeah, they're in the book as well, so if you wanted to see them maybe in a different fashion. Some of the time your book does a little bit more of writing down propositions and axioms in notation instead of in words. So it would give you a different perspective on that. And so kind of depending on what you like better, that might be helpful too. Absolutely. All right. We're going to move a little bit further along the way and talk a little bit about triangles next. So the interior of a triangle and the exterior as well. All right, so the interior of a triangle is the intersection of the interiors of the three angles. And if the point is exterior to the triangle, this happens if it is not in the interior and does not lie on the sides of the triangle. This almost feels like when we talk about our real number line. There's positive, there's negative, and there's zero, and zero is not in any category, right? There's interior, there's exterior, and there's on the triangle itself. A lot of times you talk about things having it either is or it isn't, right? This one has a middle ground, or at least a third option, which is being on the side of the triangle. This is maybe the longest proposition you're going to write down, I believe. And this references both your triangle now and some of the ray information that we've been looking at. This is proposition 3.9. This is our last proposition for just a little bit anyway. We're going to pause and do it at something slightly different. Proposition 3.9 says the following. If we have a ray emanating from an exterior point of triangle ABC, and it intersects side AB between A and B, then it will also intersect either side AC or side BC. So I'm going to attempt to do a picture of that while you're jotting that piece down. So we have a ray, and it's going to come from this point. I'll just label my ray R, since it's not got any other point vertex name or anything. And it says that it's intersecting segment AB, or side AB. So if it intersects between side A, or between points A and B on side AB, then it will also intersect either AC, that's what I drew first, or it would have to intersect BC. Right, basically saying it can't do this right? It can't miss entirely sides sides BC or sides AC if it's already intersecting side BC. It can't be like that because those two actually don't cross through side AB to begin with. So if it crosses through side AB, it crosses through one of the other two sides. The second one, this is angle R, or not angle, ray, excuse me, R. The second part on here, part B, says if a ray emanates from an interior point of the triangle, then it intersects one of the sides. And if it doesn't pass through a vertex, it only intersects one side. That seems reasonable, right? If we have a point inside, and we're going to draw a ray from that point, there's basically two options. There's the option we intersect a side, or there's an option we intersect two sides at once, which would be intersecting a vertex. Yeah, so that's a long proposition, right? A lot of language in that one. All right, so like I mentioned, this is our last proposition for just a moment. We're going to introduce another set of axioms because we've introduced the idea of triangle. So this is a good place to start talking about this. If you remember anything about Euclidean geometry from high school, you probably remember that when you talk about triangles, you're oftentimes trying to talk about proving that things are true by comparing them. Are they congruent? Are they similar? Are they, is one bigger than the other or smaller than the other? What is the comparison of two different triangles? And so we're going to talk about congruence is what we're going to talk about next, the axioms of congruence. And of course, it doesn't apply just to triangles, but it does strongly apply to triangles. So our undefined terms for congruence are congruence of segments and congruence of angles. We're going to build upon congruence of segments and congruence of angles. And of course, the interpretation that we put on that has to do with the things of length or distances or sizes, measurements, things like that. That's how we interpret congruence when we're talking about segment lengths and angles. Now, I handed out last time Euclidean geometry axioms. We talked about Euclid's axiom, maybe this is 2 times ago now. We talked about Euclid's axioms and about how Hilbert broke things down in a more axiomatic way. And so it's easier for us to work with his axioms. So we did our instance axioms. We've done that now a couple of weeks ago, maybe 3 weeks ago. And then we've done betweenness axioms over the last week or so. And now we're going to add in today congruence axioms. There are 4 congruence axioms here. And we want one more definition before I'm going to start reading through them, but this is where we're leading to, and it has to do with talking about triangles. So this is a really long one to write as well. We have 2 triangles, and they're going to be considered congruent if there exists a one-to-one correspondence between their vertices, such that corresponding sides are congruent and corresponding angles are congruent. So literally what we need is 3 pair of congruent sides, 3 pair of congruent angles. And this is our notation that we use, same one you know and love from before, to indicate not only the triangles are congruent, but it also indicates the order of congruence. A corresponds to D, B to E, and C to F. I just got through giving a test in my other geometry class, and one of the things that they were supposed to do is not only prove what the congruent, that the triangles were congruent, but the order. And some of them forgot that part of it. The order matters, right? That A corresponds specifically to D. The ordering is inherent in the way that we write it. All right, with that definition in mind, we're going to take a look then at the congruence axioms themselves on the sheet that I handed out. Yay, you don't have to write them down, and there are 6 of them, so there's quite a few, especially compared to the others where we only had 3 axioms for incidence and 4 axioms for betweenness. So our congruence axioms say the following. Axiom C1 says that if A and B are distinct points, and A prime is any point, then for any ray R emanating from A prime, there's a unique point B prime on R such that B prime does not equal A prime, and AB is congruent to A prime B prime. So I think I didn't leave space in my slides. That was probably poor planning. But I think I have enough space here, it'll disappear afterwards, that we can draw some of these out. I don't know if we'll draw them all out, but let's draw a few of them out anyway. So the first one says A and B are distinct points. And it's talking in a moment here about segment AB, so I'm just going to draw those 2 points in their segment as I start the problem, or start the diagram for it. So here are A and B, distinct points, and A prime is any point. So here's A prime, say. Then for each ray R emanating from A prime, so draw any arbitrary ray starting at A prime. So here's ray R. There will be a unique point B prime on that ray. So somewhere, I don't know if my picture is going to be legitly like, no, it definitely doesn't look like it's for real. But I extend R just a little bit further. That's better. All right, here's ray R. There is a point B prime somewhere on R. B prime is not equal to A prime. And AB is going to be congruent to A prime B prime. Now, we better hope that's true because that's how we created all of our congruent segments, right? When we were doing constructions, that's what we did. We said, draw an arbitrary line and mark a point on it, right? And then use your compass to mark it off. It's going to exist. So we were using this argument here, but it's not provable that it works. It's an assumption that we take to be true. Remember, axioms are not proven. They're assumptions that we take to be true. All right, the second one said if we have congruent segments AB to CD and AB to EF, then CD is congruent to EF. Okay, some sort of a transitive argument, so I don't think we need to draw that one. Moreover, every segment is congruent to itself. That's reflexive. Okay, so we have those facts about our segment congruences. Let's see, axiom C3 says if A star B star C and A prime star B prime star C prime, if AB is congruent to A prime B prime and BC is congruent to B prime C prime, then AC is congruent to A prime, AC is congruent to A prime C prime. So if we have these segments, and we can draw them that way for betweenness, because we're talking about the segment lengths and distance, and we have on here A, B, C. Is that the order we had them in? Yeah. And then there's some other segment, A prime, B prime, and C prime. And so we are saying that if AB is congruent to A prime B prime, like this, and BC is congruent to B prime C prime, then the whole segment here is congruent to this whole segment here. And you've probably heard that called segment addition before. Right? If you add the segments together, that they're going to still be equal as we create a new longer segment. Axiom C4 says if we have an angle, so we're moving away from our segments now, given an angle BAC, where by definition angle, ray AB is not opposite to ray AC, and given another angle, another ray A prime B prime emanating from another point A prime, there's a unique ray C prime on a given side or of the line, such that you can create congruent angles. All right, so nuts and bolts short of this says that if I have an angle, I can create another congruent angle. So here's my angle BAC. If you'll remember, we actually created these, right? We created congruent angles. We used a random ray. We used a random side length anyway. And we said, let's just mark an endpoint on there, and we created a congruent angle to it. So there's going to be another congruent segment here. I don't care whether you put B up here or down here, but here's B, here's C, and they're the primes. So if I have one segment, one angle, I can create a congruent angle. I'm able to do that. Axiom C5. If I have A congruent to B and A congruent to C, then B is congruent to C. Moreover, every angle is congruent to itself. Sounds a lot like what we just did a moment ago with segments, right? The transitive and the reflexive properties for angles. And then C6 is the most interesting, and you'll see it has another name, and you've seen it used before. It's the side angle side postulate or axiom for triangles. So it says if we have two sides and an included angle of one triangle that are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. Now, sometimes people get this idea in mind that congruence means that I only have to have these pieces of information, and in some sense that's true. But what congruence actually means is that all of the angles are congruent, right, in respective comparison to another triangle, and all the sides as well. So sides are congruent, each pair of sides is congruent, each pair of angles is congruent. So I've actually got 6 congruences inside of my triangle. And without something like side angle side as a postulate, I would actually have to test all 6 of those things every time I wanted to show that the two triangles are congruent. So it's very helpful if I don't need to test all 6, and I can actually test some smaller portion of that. And the smaller portion of that every time I'm able to do it is always 3 components. This one's side angle side with the angle included between the sides. The next thing we're going to look at is actually a corollary to that. So this is my corollary to the side angle side postulate. It says if I'm given triangle ABC and its segment DE is congruent to segment AB, then there is a unique point F on a given side of DE that creates a congruent triangle. And much like talking about congruent segments and congruent angles when we did constructions, right, our by hand constructions, this is what we used when we created a congruent triangle given 2 sides and an included angle. It's enough information to create another triangle. It's a unique triangle given the side that we want to be on, so to speak, of the line. We're going to do a couple more postulates that are directly related to these axioms, and then shift gears slightly once more today. So the first postulate we have, that we have left, this is just titled wrong, my bad. This is actually supposed to say postulate, not postulate, proposition 310. Proposition 310 says the following. If we have a triangle ABC, and side AB is congruent to side AC, then angle B is congruent to angle C. So can anybody tell me what triangle, what type of triangle this is creating? What is it? I'm sorry. Isosceles. So here's A, B, and C, and it says that AB is congruent to AC. So I have an isosceles triangle. And one of the facts that you'll remember about isosceles triangles is that they have congruent base angles. And that's exactly what this proposition says. These angles at the bottom are going to be congruent. Did I mark the things right? Oh, I just marked my sides wrong. You know what? Let me just change my letters. I'm sorry. That's what happens when you're not watching where you're marking. A, B. I can't do that way. A needs to be at the top. Yes, thank you. It's like something's wrong here. A needs to be at the top. Here's B and C. All right, so A is congruent. AB is congruent to AC, and then angle B is congruent to angle C. We'll get it there eventually. All right, we're going to do one more. This is proposition 311. It's the segment subtraction. I told you we had segment addition when I referenced segment addition inside of when we were talking about axioms, and this one's about segment subtraction. Okay, so we have A star B star C and D star E star F. We know that AB is congruent to DE. That's a portion of these two segments. And that the whole segment AC is congruent to the whole segment DF. So that must mean that the smaller portions are congruent as well. And a picture would be helpful, so I'll do that next. So I'm told that A, B, and DE are congruent. These are the small pieces I drew on the left. And the other thing that's congruent is the entire length. So the whole length here is congruent to the whole length here. It doesn't come through that well. Let me do it like this. Those whole lengths are congruent. And then, of course, that the resulting fact is that the pieces B, C, and E, F are also going to be congruent. Segment subtraction. And the proof for that would be directly related to looking at the segment addition one that we had in the axioms and talking about that from that perspective. All right, we are going to take a look at one more piece of Euclidean geometry as we wrap up this section. And it's actually referenced inside of your last piece of this notes that I handed out, and it's continuity axioms. So let's take a look together at our continuity axioms, and then we'll talk about Dedicans axiom. All right, so our continuity axioms have, or continuity axiom, excuse me, is Dedicans axiom, and it says the following. Suppose that the set L, so I'm reading off of my notes right here, and then I'll talk about this. Suppose that the set L of all points on line L is a disjoint union, sigma 1 union sigma 2 of two non-empty subsets, such that no point of either subset is between 2 points of the other. In other words, I'm taking my line and I'm going to divide it in pieces, and the way that I divide it is that there's going to be no point in between the other set, or included between points of the other set. Then there exists a unique point O on L such that one of the subsets is equal to a ray L with vertex O, and the other subset is equal to the complement, like the opposite ray. So in some sense what this is saying is that we should be able to create two rays out of a given line that don't intersect. That makes sense, right? We've talked about opposite rays and so forth. And what this is saying is that we have the ability to, in some sort of way, divide up a line. I mean, we don't really cut it in half exactly because that would somehow insinuate the pieces are equal, and I guess you could say that they are, but they're both infinite. I mean, rays are infinite, right? But that's what's going on. So Dedicans' axiom ensures that there are no holes in lines, i.e. that they are continuous. We can break them up and that they are continuous. The parallelism axiom, I'm going to read again from this paper first, and then we're going to write a fair bit more. Parallelism axiom. Hilbert's Euclidean axiom of parallelism says the following. Hilbert says for every line L and for every point P not on L, there is at most one line M through P such that M is parallel to L. It's the parallel axiom we've been using as though it's the Euclidean parallelism, right? All along as we've been talking. It's actually, though, Hilbert's version of it. So we're going to talk a little bit about the parallelism when we talk about the comparison of the way that each of these two men wrote this parallel postulate. So Euclid's parallel postulate versus Hilbert's Euclidean axiom of parallelism. The statement that there is at least one line parallel to every line through a point not on the line can be proved from the previous axioms. That is, that the previous axioms rule out the elliptic parallel postulate. That's what Euclid wanted to be true. He wanted his postulate, I shouldn't say that. He wanted his postulate to be a proposition. He wanted it to be provable. He wanted to be able to take his previous four axioms and prove it, not just have to assume that it was true. And if you could do that, it would in fact rule out the elliptic parallel property that we have talked about as well when we've looked at projective planes.
Like through Hilbert's Euclidean axiom parallelism, it says there's at most one line. But Euclid wanted to prove that there was at least one line.
He wanted it to be able to be proven, yes. Hilbert assumes it as an axiom that it can't be proven, and he writes it differently. Does everybody have this one written down? Are we good? Oh, almost. So for hundreds of years, mathematicians tried to prove that this worked. They tried to prove the Euclidean parallel postulate given the other four postulates that Euclid had created. In the process of doing that, it was actually discovered the Euclidean parallel postulate is independent of those postulates, i.e. it can't be proven. So how exciting would that be to work with your advisor for a whole semester trying to prove something, only to find out in the end that it's something you can't prove? You know, mathematicians did this for hundreds of years. All right? So what this means is that we have to take the Euclidean parallel postulate as an axiom in order to obtain the Euclidean geometry that we have done all through high school. It actually can't be proven. So what we do instead is we use our instance axioms, the betweenness axioms, the congruence axioms, right? These were all the Hilbert things, and Dedicans axiom, that's for continuity, and the Euclidean parallel postulate. And in doing so, we obtain all the results in Euclidean geometry. Geometry from high school. In the first day of class, I handed out to you, I think it's about 5 pages or so, front and back, something like that, in a couple different forms, all kinds of Euclidean postulates. Not postulates, theorems. Euclidean theorems. And we get all of those by having these axioms. There's nothing, well, there's not nothing different, but Euclid's 4 postulates before the parallel postulate are broken apart to create the incidence axiom, the betweenness axioms, congruence axioms, and Dedicans axioms. A lot of times it's easier to use portions of something if they're broken apart into smaller bites. And so that's what the incidence, betweenness, and congruence and Dedicans axioms do, is they break down Euclid's first 4 postulates into smaller chunks of material that are easier to use as we need to use them. But we use the Euclidean parallel postulate, postulate number 5, in addition to all of that, because it's not enough. Using just those pieces of information, we actually obtained the possibility of having the elliptic parallel postulate hold true as well. We created an interpretation that was a model that worked for that. We did it by placing the Euclidean plane on top of the hemisphere. So we don't get it for free. It's actually something we have to take as a given piece of information. We can't prove it. Is anyone still writing on the screen? Am I good to continue? Okay. Our model, the one that we use all the time, we know and love, is the Cartesian plane. The Cartesian plane is a model for Euclidean geometry. It satisfies all of Hilbert's axioms, including the Euclidean parallel postulate. And it looks something like this description. Given an arbitrary line, y equal mx plus b, if we had a point not on the line, the point referenced as the coordinate AB, and there exists a unique line parallel to y equal mx plus b through that point, and its equation would actually be y minus b equals m times x minus a. And this is what we do in, usually we see it done first in algebra or a pre-algebra context. We talk about the fact that parallel lines have equal slope. We talk about the fact that perpendicular lines have negative reciprocal slope. We usually do them about the same time. And we create equations of lines that are parallel or perpendicular through given points. All right, I showed this last time. Is everybody, I'm sorry, we still have a couple people in the right. Are we good, Shayna? You good? Okay. I showed this last time, but just as a reminder, you do have some homework next time to read pages 119 to 129. And there's a couple of problems on there. Problem number 20 has, I know it has multiple parts. I can't remember about 24. But so don't let that fool you. That's really not just two problems. There's multiple things within those. And let's talk just briefly, and I'm going to keep this audio recording going just to make sure everybody can reference it if you do miss something that I say. Just talk briefly about next week. We have this due on March 13th, which is Tuesday. And on Tuesday, we're going to also talk about the final, or not final, I keep saying final, the midterm exam, which will be on Thursday, okay? There will be two portions to the midterm exam. One portion will be take home, and I will give that to you on Tuesday, okay? And you'll return it to me on Thursday. The other portion will be in class on Thursday, so it will be timed in a timed environment. It won't be something that I expect you to have memorized everything. There will be portions of the materials that I've given you where I will talk to you Tuesday about what you're able to bring and use on that test, okay? But it will be done inside of the classroom. Some of the things that we've done are not necessarily lecture-based. We've talked about things outside of class, like the constructions that you've done, and you did a considerable amount of that. We spent, I don't know, at least 4, I think it was like 6 class periods of doing constructions in class. You're going to do some constructions on your test, okay? And they won't necessarily be the exact constructions that you've done in class, but they will be related to it, those kinds of ideas. So please bring your compass and your straight edge. If you don't have them, I'll have my box with me here, and you can use one of mine. So you'll have some of that on there. There will be lecture and components of what we've done in here. There will be components of things that you have learned to do inside of GeoGebra. I'm not exactly sure how I'm going to test that yet, but we will be doing something of that nature on your test as well. So it might be that I have you do something inside of GeoGebra for the take-home portion. That's probably what it will end up looking like, since that's done on the computer instead of you bringing that to class. I haven't made the test yet, so I don't know how much more specific I can be right now, but do you have any general questions maybe that you'd like to ask?
Most of the basic instructions you can find online too.
A lot of them you can.
I didn't write down the things.
You can find, I didn't do any audio or video recording for that, but a lot of them you can do YouTube videos of other people doing them. Like if you go out to YouTube and you Google, create a triangle using side angle, side postulate, something like that, you'll probably see several YouTube videos pop up. So if your notes are not quite as thorough as you wish you had taken them, or if you're just not sure if you could recreate it if you were asked to or something like that from what you've written down, yeah, lots of them are out available on YouTube. Yeah. Anything else? I will have everything you've turned into me so far finished and graded by Tuesday. So right now what I'm lacking turning back to you is the affine projective plane paper that you gave me. And then the last homework problem, I believe that those are the 2 assignments I still have from you. And the GeoGebra problems number 2 that you guys turned in, so those will all be graded. I think it was Seth that came and asked me questions about how do I know what I did or didn't do right on GeoGebra project number 1. And so if you aren't aware, were you able to access that, Seth?
Oh, no,
After we
because
talked?
Canvas wasn't working.
Okay. I uploaded to Canvas inside of where you uploaded your assignment pages that you turned in another page. So you should be able to access my remarks. Kelsey's nodding. Have you seen them?
Yeah.
Excellent. So they are there. Like, since I haven't actually seen your perspective of Canvas, I was like hoping that I did that right. So if you're wanting sort of some feedback about maybe tips or tricks or things that you did right or didn't do well or something like that, you should be able to see those inside of Canvas linked to that assignment, the feedback from the first set, and there will be feedback done the same way from the second set, okay?
For the test, are we going to need to memorize any of the definitions, axioms,
No.
or any of that? Right?
No. You won't be expected to have any of the things memorized. I'm far more concerned with your ability to reason through something than to simply regurgitate it at this point. So for those of you who are in education classes and stuff thinking Bloom's taxonomy, right? Bloom's levels of thinking. That's kind of what we're going for here, is some of the higher levels of thinking.
problems on there that are like similar to the logic questions quiz?
There will be. You may have problems on there where you have to decide if something is a model for a specific type of geometry, given certain conditions. You could do something where you have to decide if you've got an affine plane, and kind of like on the last project that you guys did, the worksheet. You could decide if you do in fact have a model for incidence geometry, does it have a specific parallel postulate? If so, which one? You could do things like that. That I think was what you guys looked at, explored on your last homework assignment. Things like that. I could ask you to prove some of these different postulates that I have moved ahead and sort of just generally described maybe in class how we would prove them. So you could be asked to prove something more specifically. The stuff we did with the end here about segment addition and segment subtraction postulates, we could be dealing with some of that potentially on the test. So it will be applications of the different facts that we've worked with and being able to reason through, what do I do with this information? How do I piece it together? Obviously, inside of class, I'm not going to ask you something that should take you a page to prove. That's not realistic. So if I want you to do something that's going to be a more considerably lengthed proof, it's going to be something I would give you on the take-home part of it. I'll say it now, even though you guys know this to be true, but the take-home portion should be done independently. If your work looks identical to somebody else's work, we got issues. And we're going to have issues with your grade, and you're going to be sad. So please make sure that your work, as you're working on the take-home portion, is your work, and not, group work together thought about. Okay. Anything else? I suspect things might come to mind between now and Tuesday. If they do, jot them down and ask them in class. I'd rather you ask them in class than to send me an email at this point, just so that everybody has the ability to hear this answer to the same question in case they didn't think to ask it. I know Felipe won't be with us next week, so I'll make sure that I audio record just like I am right now, anything that I do say, so that everybody has the same chance to hear the comments that are made.